the Cienega Creek watershed since 2014. I started working with Dr. McIntosh. We looked at isotopes, stable water isotopes, and age tracers in Davidson Canyon, Hilton Ranch Road area. That's where I did my senior thesis work. And then we just expanded it out into the broader watershed, specifically the upper Cienega Creek area that encompasses the Los Cienegas National Conservation Area. This is kind of an accumulation of all of that. So for our research motivations, when we initially started looking into this area, there is a limited amount of baseline data specifically on water quality and the hydrologic conditions of the watershed as a whole. We all know there's increased demands on groundwater through pumping, land use, lots of talk on climate change, and mining, and the Los Cienegas Conservation Area is a precious little spot where, you know, disrupting the ecological balance could have some serious impacts. And then providing scientific information for land management decision makers. So our research questions are, what is the elevation and seasonality of recharge? We're going to use stable water isotopes to answer that question. What is the source of sulfate in the groundwater, and can sulfur isotopes be used to identify flow paths? Just south of my area that I will show you in a moment and north, there is high sulfate in the waters, and so that led us to ask this initial question is, you know, can we see the sulfate in our area? Also, what is the residence time of groundwater across the basin, and are there areas of recent recharge? And what's the nature of the hydrologic connection from the Santa Rita Mountains to the wetstones adjacent Cienega Creek? So the way that we went about this is had a team sampling groundwater wells, piezometers, springs, and from the precipitation collectors. We took field parameters, used age tracers, stable water isotopes, and major ion chemistry to come up with our conclusions. So this is the area that we use as what we classified as the Cienega Creek watershed. This map was put out by Pima County, and our area of interest is right here with this area that we call the swath. And these are the sample sites. So my area is very focused on the groundwater, not so much the surface water. I look at the precip buckets that's in the high elevations of the mountains, all the way down to the lower basin. And then I stop at the springs, which is what creates the Cienegas themselves. But this particular picture is sampling because the people who put in the time for all the sampling was tremendous and a lot. And we have a huge composite data set that is awesome. So can we identify altitude and seasonality effects in the watershed using Delta 18O and deuterium? In the Tucson Basin, Dr. Isto has an excellent 30-year record of precipitation out of buckets, and you can see a seasonality trends as well as elevation shown here in this. However, when I plot my data against the data there, we have a lot of variability and it doesn't necessarily make sense. The one thing about the record that's from the Tucson Basin, the Santa Catalina Mountains, is that you can clearly see the trend, and it is a longer record. Our record is about 4 years. We do have good elevation change. The other thing is that the Tucson record is, amount averaged. So ours is not. It's just the value that was in the bucket, and that's stable. So you can't really see with ours. There's another study from the Cienega Creek watershed area where they have average summer and winter, which is summer here at the top, mountain versus basin, and winter, mountain versus basin. And then when we plot our data, that most of it falls within the winter. The other interesting part of this is do we see an evaporation trend within the recharge? And so if the data points plot in the direction of these arrows, then we can identify some evaporation happening within the swath. And with points that are plotting above the meteoric waterline, we can identify potentially it being an evaporation during winter rain recharge. That's out of a study that was done in Oman, where that is why we see this. The other thing I want to say here is that the local meteoric waterline that I have identified here is from our precip data, which you saw was quite variable. What that means is from year to year, that local meteoric waterline can really shift and so there's a potential that if I had a 30-year record, maybe that local meteoric waterline would shift enough to capture all the data, but you know, we do what we do. So, onto the sulfate story. The boxes here are from Dr. Isto and his student Gu. They did work in the Sonoyta Creek area, and they identified these regions where the sulfate was gypsum dissolution, atmospheric, or pyrite oxidation. And I plot my data against the same thing. Their data is the open circles, and can't really see too much in that, so we went ahead and took a different route, plotted the sulfur isotope versus 1 over sulfate, because the waters in our area are not high in sulfate, unlike the Sonoyta Creek area and the lower Cienega area that do have the high sulfate. So in order to emphasize that low sulfate, 1 over sulfate is a better decision. And these regions over here are the sulfur isotope regions that are the same as those boxes. So you have gypsum dissolution here, you have atmospheric signature here, and you have pyrite oxidation here, based on the ranges of the sulfur isotope value, and most of the groundwaters that we're using for this study fall into the atmospheric signature. My project is focused on a very broad scale. We're looking at this because of the lack of baseline data. I'm not getting down to the minutia. So yes, there are some outliers, but I'm not focused on that. I'm focused on the bigger picture. People can come on after and focus on the minutia, which would be awesome. Then looking at the Cienegas themselves, because that's quite an interesting area and what most people in this area particularly care about. And what we can see based on where the data points plot as a sulfate to chloride ratio versus the delta 18O, most is plotting in this basin groundwater range. In the Tucson Basin, that sulfate to chloride ratio range, that's what that value is in the Tucson Basin, again, is the same as this basin groundwater area that we see. Again, the open black circles, those are from the Sonoyta Creek. So there is a source of rocks. The water-rock interaction is creating additional sulfate into the water that I'm not experiencing in our area of the swath. So then we're going to ask, how old is the water, which is something of interest. And we went ahead and looked at the area along Gardner Canyon. And what we found was the zeros do not indicate zero tritium. What the zeros indicate is below detection limit, which is 0.05. That's our detection limit. And our tritium samples were below that, which is an indication that you do not have modern recharge. However, this 1.7 and this 2 is detectable tritium. There's also some detectable tritium in the Las Ciennegas National Conservation Area as well. That just means you have a mix. So you do have some modern recharge mixing with older waters. It's quite interesting that at the recharge zone, which is at the mountain front where the Santa Ritas are, we have a spring and a well, and the well is right next to a wash. And we have a 0.9 and a 0.8. That well may be a product of the spring because of the hydraulic gradient and the way that it moves into the wash. But it is still right there, and we have very low tritium values, which you would assume with being in the mountain front, that you would have a mixture more like this 1.7 and 2. So then we were questioning, well, why is that? The other thing is for modern tritium values, if you had a cup of water outside right now and you measured the tritium in it, it would probably range somewhere in the 4 to 5. So again, 1.7 to 0.8, these are low values. So we did a cross section right here across Gardner Canyon to take a look at, can we identify potentially in well logs what's going on. So what is of interest here is this clay layer. But I think we were a little surprised at the magnitude of the clay layer from the mountain front all the way into the basin. But that 2 tritium unit well, you can see the clay layer really crops out right at that point. So there's probably an opportunity for the recharge, the rainwater to recharge more easily, if you will, into the ground, opposed to this thicker clay layer where it's a little more obstructed, and then this alluvium on the top is quite thin comparative to maybe other areas in this southern Arizona. So we also I thought, well, what about the carbon-14 raw data values versus the depth of the well? And this is in the Las Ciénegas National Conservation Area where the depths are quite deep. These are exploratory wells by Animax that was done in the 70s. And we have extremely low carbon-14 values. I mean, this water, if you used a radiocarbon dating and you were thinking of it as decay, it's on the measure of 20 to 30,000 years old. Whereas this well here that is still below what maybe modern carbon, if it were again measured, would maybe be in the range of 104, 107. We're at 84.7 at this mountain front well. That's that same well that has the 0.8 tritium value. So, what did we learn from this study so far? Is that our current precipitation data does not show us an altitude or seasonality effect across the watershed. Sulfate in the basin is mainly derived from precipitation. The Ciénegas and the Las Ciénegas National Conservation Area are groundwater dependent. Groundwater was recharged prior to the 1950s for mostly across the basin. And long residence time in basin groundwater is due to the importance of that thick clay layer across the basin. And groundwater across the basin comes from mountain block recharge. This is, I'm going to say, more of, at this stage, still a hypothesis. And the reason is that it's at that recharge zone, but until we can get a better end member in the mountain itself, then I can have a better identification. Or I would feel better about saying that definitively. So, future work. It's interesting to find out why the Ciénegas are where they are. This is Empire Ranch right here. And there are some previous studies that show that there's this potential clay layer cropping out right in this region where the black dotted line is. And so that geophysics class, the poster that I have over here, this is the area that they targeted. And some of this is related to the poster and to our hypotheses of seeing this clay layer and its importance, especially to the Ciénegas themselves. This is gravity data that shows this shallow bedrock a bit north of the area. So one of our hypotheses is that there is this clay layer that crops out at that dotted line. And then you have shallow bedrock going subsurface. So the water may be traveling below this thick clay layer that then crops out, which then opens it up, and it has a conduit of the bedrock to then travel to the surface, because that is the area where the Ciénegas appear. And the bedrock crops out just a little north of that. That's why there's this possibility. Okay, so in order to get a better end member of that mountain block, I am going to be going into at least one cave in the Santa Rita Mountains. The plan was 2. However, permitting has taken a bit longer than anticipated, and I hope to be finished by the end of this summer. So we're going to try to find the tritium. The plan and the hope is that there is modern tritium in this water, and then we will have a better idea of an end member that then can better constrain the carbon-14 values. Making additional cross-sections is important. That initial cross-section that I showed you really opened my eyes up to what was going on subsurface. And then construct a conceptual model. The conceptual models that exist right now are best to our knowledge, but I think we can improve on them, and I think our study can make them a little bit more refined. I also want to draw your attention to some related work. Erin already talked a little bit about her work, which is that first, which is her posters right over here, and she's really focused on the Las Ciénegas National Conservation Area. And then what's exciting is that kind of my project had some questions that Pima County was interested in the lower Ciénega, and so there's going to be a master's student coming after me who's going to be doing that larger, and so it's going to be kind of the same questions using the same types of techniques to answer the same idea of what's going on there. And what's really interesting is geologically, that area is completely different than my area, so there's going to be a completely new story. There are some serious people to thank. I tell everyone I know that this has kind of like been a pro bono, if you will, project. This has not been a normal graduate student project. I did not come in with funding. We did not have, you know, NSF and all this stuff. It was just a labor of love. We came to this meeting in 2014. We met Ron and Andrew, and it was just, they just started a project. We have received a little bit of funding from BLM and Nature Conservancy, but it's been small in the respects that it's needed to go to the analyses, not for paying a student. And I would not have been able to do this without that. And it's, sorry to be emotional, but it's been awesome because I have wanted to do this for 20 years. And I have a little thank you for these people. It's a really big deal for my life. So, Ron and Andrew, are you here? Ron, thank you so much. I need to put these people's name up. Without the funding, this would not have been even remotely as thorough as it has been. So Gita and Jean Marie, thank you so much. And tirelessly, the undergrad Erin, she filtered so many samples, and honestly, that was not even close to fun. And then ran alkalinity, and that was awesome. And then Dr. McIntosh, there's not enough to say about her putting up with me for the last 3 years, and how grateful I am. So, thank you all for indulging me and letting me do that. And I guess there's questions later, not now, right?
Here's our questions. Are there any questions for Rachel? Over here.
If I'm understanding your collection, that means groundwater means water that would be in aquifers under the ground?
Yes.
Okay, how deep did you have to go to get your groundwater sample?
Well, I use domestic wells, so at people's house. So those yellow circles that were on the map were people's houses. So it was just a matter of knocking on the door and trying to look unoffensive and water, and then they said, okay. So, thank you.
Yeah, can I make just a brief plug related to that? Rachel mentioned our new study from Davidson Canyon to the lower Ciénega Creek. So if you know of any homeowners that are along Hilton Ranch Road all the way down to the highway. Please contact me. We're looking for permission to sample wells starting this summer.
Good question. I'm not a scientist. I'm just interested in this. Did you look at how much the water is being recharged compared to how much water is taken out?
No, that was not a part of
Because
my
that would
study.
be really important for all of us here.
Yeah, there are some previous studies that do talk about transmissivity, which is something of the thickness of the aquifer. There's also some studies that talk about that when Animax was doing its exploratory wells, there's some things from the 70s, so if you were interested in that, I think you can find a little bit of information. It's not updated, which I think would be very helpful, but you could at least get some idea.
And let me just say a basic comment about basic groundwater hydrology. What recharges, at higher elevations and along the washes comes out as stream flow and the water the plants use along the basin center. So they usually determine recharge by looking at how much is coming out as surface water. And not a lot in that basin because we don't have a lot of surface water. As we know, those places are really important.
Okay, well, thank you, Rachel.